What's up, everyone? Brandon Jennings here, head of programs at TKS. We are now live, so I'm going to jump into hopefully a fun hour of different emerging technology related discussion. So the premise for this conversation is TKS is it's a 10-month program we run basically with students like you from all over the world who want to learn more about emerging tech and science. And we essentially train you on how to build projects in frontier areas of tech and science. And it's sort of a pretty involved process. It's something that is really beneficial for a whole host of different future outcomes, right? If you want to go work in for a technology company, start your own company, understand how technology is going to help solve big problems in the world, there's a lot of linkage to sort of project-based learning, developing domain-specific skills en route to understanding how technology is really going to make an impact. So that's kind of what TKS is. I'm going to get into that more at the end, but the purpose of this is not a TKS info session. This is actually just going to be a deep dive in a bunch of cool stuff in emerging tech and science. So Sydney and the crew basically invited me to join. I think Sydney's also here. So if you guys have questions, feel free to put them in the chat or in the Q&A field on Zoom. And we'll definitely have some time at the end for questions. And I'll sort of be checking the Q&A field throughout and addressing anything that seems relevant at the time. Okay, so without further ado, I'm going to jump in here, share my screen. The topic for this, and I know that we sort of had like some wording around this, but I really want to focus on lesser known, and I put that in quotes. I'll kind of explain what I mean by that. Emerging technology opportunities through 2030, so in the next 5 years, right? And the reason that I wanted to take this angle with the talk today is because we're hearing a lot about AI, and that's the front and center technology of the moment is large language models that I'm sure all of us on this call have used, whether it's to help on our physics homework or help understand how to like fix something that's broken in our house or on a bicycle, something like that, right? And that's all a leading indicator on how the world's going to change in the next 5 years, but there's so many other things that are happening outside of advancements in AI, or in some cases, things that are going to be powered by advancements in AI that I want to focus on for this talk, right? So the reason I used lesser known, and I sort of put that in quotes, is because right now there's so much emphasis on large language models that I want to kind of shed a little bit of light on some really cool advancements that are happening elsewhere in other fields. So real quick, a little bit about me. I'm a manufacturing and operations person. I'm now running product and programs for TKS. As I mentioned, TKS is our 10-month program learning how to build projects in tech and science. Studied mechanical engineering at MIT, ended up working as a aerospace mechanical engineer for SpaceX, for Raytheon, for a couple aerospace companies. Ended up going into sort of the business world, worked for McKinsey, which is a big global management consulting firm. Then I got into like this, basically the startup ecosystem in New York. I list Bowery here because it was the place I spent the longest amount of time, but I worked for a couple other fintech companies, and basically I would get hired as the one of the first employees to help translate the like lab scale engineering work to the big scale stuff once the company's raised money. So that's kind of my background. And I really like what I'm doing now at TKS because I essentially design the curriculums and the programs that we run. So, I have to stay very on top of everything happening in the world of tech and science so that we can help translate that into all the educational material. So the way this is going to run is I have like 6 or 7 different areas, and then I'm going to run through a few different examples of cool stuff that's happening in each of those areas. And this is kind of biased, right? Like because I come from I think hard tech is really cool. Hard tech being hardware, robotics, things that are not just software. And so you're going to see that in some of the examples I run through is, some of them have to do with AI as they relate to different hard technologies. So the first place I want to stop is in manufacturing. And now I know this isn't really an interactive format, right? So I unfortunately don't have the ability to like call on people and ask questions and things. So I'm just going to be speaking, and that's okay, but I'm going to keep a look at the chat. So if you guys have any questions, feel free to drop in the chat. Manufacturing, as we all know, is making goods. So you can think of a factory like a big black box. Raw inputs come in one end, finished goods come out the other end. And there's a very understudied potential, in my opinion, on how to use AI, neural networks, large language models, reinforcement learning on how to do manufacturing better. So I'm going to give you a few examples of what I mean by that. Example number one is what's called generative design with physics constraints. If you've used ChatGPT, let's say you can prompt it to give you a picture of a futuristic looking chair, right? And you can type that in. VO2, whatever the model is, will give you a rendering of a futuristic looking chair. Now, the problem is that if you wanted to go manufacture that chair, first of all, it's not a 3D file. So, but there are things out there. There's a company called Zoo that, takes the Google output and turns it into a 3D file. But the problem is it's not studied under the lens of like realistic physics constraints. So like literally the most advanced thing right now is this thing called Lego GPT, which was out of Carnegie Mellon, which is literally a large language model text to design system where you can say, hey, I want a Lego model of a duck, just as an example, and Lego GPT will give you a real Lego model of a duck. Now, the thing that's cool is, Legos are pretty simple, right? But there's a lot of constraints that need to be satisfied for a Lego to be a Lego. Like number one is the linkage of the actual Lego pieces together, right? Like you have to join two pieces together and there's different pegs and holes that need to be kind of fit in. Thing number two is like gravity. If you have a duck that is in the center of mass is not over the stability platform of the feet, then it's going to tip over. It's not going to work. So like for if you imagine these non-text or video or picture use cases of AI and generative AI more specifically, like I think it's going to be really interesting, and there's going to be a lot of money that's made by companies that figure out how to bring in realistic world constraints, physics constraints, and so forth. So that's kind of thing number one. Thing number two, and I have it listed here, is machine code as plain text. So right now, it's actually really hard to take and I know most of the people listening to this are in high school, but those of you that want to go study, let's say like robotics or mechanical engineering or something, you're going to go off and you're going to go to university probably, and you're going to learn how to design things in CAD and then how to translate that CAD file to something that can get manufactured, right? If you think of, let's say we're building a little metal part of an engine. You design it, and then it's like, okay, I have to go make it on a mill or a lathe or something. The way you program that mill or that lathe today is by actually going in and establishing the machine code. And so it's kind of a lengthy process, and there's things that can automate it slightly, but where we're going in AI world is basically being able to hit print metaphorically, and then having machine code. In other words, what machines do I use? What calibration and tolerances do I have to program into those machines for the part to be right? All of that can be automated. Now, that's actually very hard to do, and it's sort of like a non-trivial thing. So those of you that are interested in, I guess, either business opportunities or just cool research opportunities in AI, I would definitely encourage you to look more at we'll call it the life cycle between design and manufacturing. So you make something cool. Manufacturing, it's usually the hard part. And those of you that are like Tesla fans or SpaceX fans know that this is a big thing that, Tesla and SpaceX say all the time is like the making the cars is the hard part, designing them is the easy part. So there's just like a ton of opportunity there. Same thing with factory process flow automation. Like, so let's take Apple for example. There's literally tens of thousands of employees that work at Apple, and I've often asked myself the question, what do these people do all day? And the reality is that there's such a large contingency of people that just focus on little problems that happen in the manufacturing process of things like the Apple Watch and the iPhone and so forth. So one example is, Apple produces a lot of their stuff in China, now more in Cambodia, Vietnam, places in Southeast Asia. Machine calibration is a huge problem. So in other words, you go and you have to constantly calibrate the machines that make the parts. Those machines are not perfect. Manufacturing is sort of a science of managing imperfection. So those machines will, fall out of calibration, it's called, which basically means, you want to cut something to 0.0001 millimeters, and you accidentally cut it to 0.0002 millimeters because it's out of calibration, right? So there's this concept of listening and learning that is, with more AI powered sensor technology, you'll be able to essentially listen to machine health, understand when machines are falling out of calibration, and react to that accordingly, whether it's shifting the design parameters, changing that machine code that we talked about in step two, and say, hey, instead of cutting this thing to 0.001, we actually have to adjust it because the machine's falling slightly out of calibration. And so these things are pretty niche. And I know this, but I think just high level summary here is anyone who wants to find cool opportunities of building projects in I would not encourage you to go into like chatbot related things and generative video related things. They're just, those markets are super saturated. I think something like AI in manufacturing is much more robust. Okay, the next stopping point here is, and this is again, cool emerging technology trends in the next 5 years, is what we'll call like the robotics revolution 2030, 2030 being the year 2030. So 5 years from now. So if you ask me what's going to happen in the next 5 years in robotics, I think it's going to be an explosion of new neural hardware and sensors that allow robots to function more as humans. Now, those of you that know robotics, like if you go and maybe you've seen like videos of Boston Dynamics or some of these new Chinese robots, you'll say, hey, or even the Tesla stuff, Optimus, you'll say, hey, there's already robots that are functioning like humans. And what I would argue is they give the appearance of functioning like humans, right? So one example is, an Optimus robot, that's the Tesla robot. If you look at the videos that Tesla puts out, they're doing very repetitive tasks. And so the sensors they're using are, cameras for the eyes, microphones for the ears. And if you say, hey, like go pick up a coffee mug, it'll be able to scan the room, use kind of, language or visual processing to say, this is a coffee mug, and then grab it. It's good, right? That works. It's doable with the hardware on board. Now let's imagine another case where you say, uh, I want this robot to fix my bike. Like those of you that ride bikes, I'm a cyclist, so all the time I'll hear some sort of weird noise, a grinding on the chain of the bike. So you bring it to a bike mechanic, and a bike mechanic will kind of look over the bike, run a bunch of tests, and then ultimately triage and diagnose what's wrong with the bike. Right now, we're sort of orders of magnitude away from a robot being able to do that, and the reason isn't because a robot isn't kind of machine smart. It's because diagnosing and triaging a bike it's like a multi-sensory thing, right? You have to listen to and sort of triangulate different sounds, whether it's like creaking of the frame or rubbing of the chain. Sometimes you have to be able to smell things. So smell like a burning smell if something's rubbing and creating friction. And so, like there's all these different sensory capabilities that a human has that we're not even close to humanoid robots having, right? We're getting really good at the brain, in other words, and that's neural networks and so forth, but we're not really getting good at like the actual hardware or sensory capabilities themselves. So what I would encourage, and I do encourage, like TKS, our students are working on a lot of these types of projects. People who are interested in robotics, I always encourage you to start figuring out different new novel sensors that can act as like a nose, right? Or ears or touch haptics. Fun fact is the hardest thing to design on a robot is actually the hand, because your hand is one of the most sophisticated it's one of the most like sophisticated things on your body, but more specifically from a like neural sensing perspective, you have an incredible amount of sensory capability in your hand. You can sense extremely low pressure in your hand. So there's no, like, we're not even close to be able to design like a replica for the human hand. So there's just like tons of opportunities in robotics, and yeah, if anyone is interested in like learning more, we do a lot of this kind of stuff. But if you want to go build stuff in robotics because your eventual goal is to like, I don't know, work for a cool robotics company, definitely focus on things like sound, smell, etc. Right? Um, yeah, but yeah. there's a group out of MIT that's actually doing kind of the most work on sound processing. And sound processing is when, and if anyone's like really into math on this call, sound processing is pretty cool because it's all, it's all like signal processing, kind of like Fourier transforms and things like that. But you have, like, it's actually really hard. We're like amazingly good at being able to triangulate sound very quickly. And that's really, really hard to do with kind of conventional hardware that we have on robots and things. Okay, another big thing that's going to happen in the next 5 years is there's going to start to become more new novel innovations in material science that actually start to do real things. So I'll give you a couple examples here. This is certainly not exhaustive. Example number one is self-healing materials. So this is like a real thing. Sounds science fiction, but it's like actually a real thing. It's on the lab bench works. Now it's a matter of just getting the cost profile down. Like materials that can heal themselves. It is what it sounds like. So, for example, if you're Boeing building an airplane and you have something that comes into contact with the fuselage and causes like a small imperfection, like theoretically, you can design materials that'll actually close up that imperfection and fix it, right? It has to do with like the polymerization of materials and how all that stuff can sort of like return to original form after imperfections and abnormalities happen. So really cool research being done in a whole host of different institutions. But for anyone who is interested in like chemistry, material science, I think self-healing materials are really cool and starting to actually become real things that exist in the world. Metamaterials is another thing. So metamaterials are basically materials that that we're able to design outside of properties that exist in the real world, right? So for example, there's a lot of work being done on next generation antennas. So like 6G and like right now, if you have like an iPhone 5G, well, the next evolution of that is 6G. And what people want to do, there's a lot of cool stuff being pushed here is essentially having really hyper compact antennas that you can just put everywhere, right? So if you think of like the Internet of Things, I could have an antenna on my coffee mug. I'll use the coffee mug as an example again, that like just gives me real time, super low latency, super low energy feedback on like how hot my coffee is, right? I have a little temperature sensor in here, plus like a little 6G antenna, can communicate locally, either on the edge through a network, and cool, sounds really great. Not the most interesting use case in the world, right? But that's sort of the example that I'm offering. So in terms of like military use cases, more consumer use cases, there's a lot of work being done at cool, like, think of like the Caltechs, MITs, Stanfords of the world on metamaterials, being able to design materials that, think of like an invisibility cloak, like, materials that actually allow light to pass through them kind of thing. Another example is like superconducting materials. So there were a couple headline breakthroughs in this was like probably 2 years ago at this point, but basically headline breakthroughs around superconducting materials. Now, superconducting materials are kind of what they sound like. They're extremely good, basically zero energy loss. Conductors were, in order for this to work, you need to cool things to basically absolute zero, a ton of energy required. They're extremely expensive. So we're pretty far away from being able to do this at scale. But with advancements in AI, quantum computing, some of these other things, we're getting to a point where like we can on the horizon sort of see superconducting materials actually become a thing and potentially have commercial applications. So one example of just if you're thinking what's the mental model for like a use case, one example is electrical transmission lines. So depending on where you live in the world, you got like power lines that come into your house. Those are called distribution lines. You've got generation that happens, whether it's solar, oil, coal, whatever, and then you've got distribution lines that go from the generation to the distribution to the transmission. To the distribution. So the transmission lines are like the big things that you see sometimes in neighborhoods and so forth. So theoretically, if you were able to have superconducting transmission lines at a zero energy loss, well, right now you lose. I think it's somewhere between 10 and 20% of all electricity that's generated. We just lose through essentially friction in the lines. So that's a huge number if you extrapolate that out globally, right? So like even being able to, I forget about like the superconducting thing. If you're able to make more efficient transmission lines, like 1% more efficient, you'll save like an astronomically high amount of uh, money, number one. But if we're thinking of this in environmental terms, like carbon emissions from just like saving 1% of the friction loss on transmission lines. So material science innovations are really cool because they intersect these things at several points. Another cool thing, this is probably the most hardcore thing happening right now aside from AI is quantum computing. So quantum computing, if anyone's not familiar, is basically, we have like traditional computing, which everything is represented in bits and bytes, zeros and ones. Quantum computing, instead of a bit, you have something called a qubit. And instead of it just being a zero or a one, it's able to be basically zero, one, or anything in between. And sounds kind of weird. It sounds kind of fancy, whatever. The way to think about it and what that actually means is that you're able to parallelize things at crazy levels. So you hear quantum computing mentioned in the same sentence as like cracking Bitcoin encryption, or like security codes and passcodes are just completely hacked like everywhere all at once. Being able to simulate uh, the Big Bang or natural events, right? And so like the promise of quantum computing is that all of a sudden you go from having to run everything on sorry, I'm just keeping an eye on the chat here. Yeah, I don't think I'm having audio issues, but let me know if I am. Using supercomputing for everything, which just runs everything in series to be able to parallelize massive computational sets, right? Like today, and this is kind of an interesting factoid, is like caffeine. I keep using coffee references, but I'll use it again. Like the caffeine molecule, even the world's most sophisticated supercomputer can't model the caffeine molecule like in the wild, like build the molecular structure and model how it's going to interact with other compounds and things. That's way too computationally intensive, even for the world's best supercomputers. With a quantum computer, you can do that because you can parallelize all the interactions and you can essentially you're simulating the physical environment. So the two big things that are going to potentially happen in the next 5 years are, number one, you're going to have major gains in the error issues with qubits. So like so a qubit's tough because you're essentially just, it's like particle physics. So if anyone, yeah, again, like for the math people out there, for the physics people out there, it's like quantum mechanics and quantum computing are linked. And essentially what you're doing is, instead of a bit or a byte as like an electrical gate, you're studying particle behavior. And so these systems are extremely noisy. And if you look at companies like Google has a big quantum lab, IBM has a big quantum lab. Even Amazon has, like, they're trying to figure out quantum computing. Like Microsoft, right? All these huge tech companies are investing a lot of money in quantum computing, and the thing that they're spending the money on is, how do I make less noisy qubit architecture? So that's the main problem we need to solve, which is why I highlighted it here. So for anyone who's interested in quantum computing, you can basically educate yourself right off the bat on just like what are the latest methods for reducing noise in quantum computing systems and in qubits. And so like if anyone reads Ars Technica or Engadget or anything, you might remember that Microsoft came out with this I think it was called Marjorana or something. It was like a new qubit architecture, and it was all about this, right? Basically reducing the noise in qubits. And then the other thing that's going to happen in the next 5 years, this is already kind of happening, but hybrid quantum classical systems are gonna become more of a thing. Companies like D-Wave, they're kind of the OG startup in the space, and you're going to see more of that kind of thing happening, which is basically like actually usable quantum computers. Like me and you could go use it. So if you're interested, IBM has a thing called Qiskit. You can go on, play around, but there's still a lot of work to be done in how these algorithms are developed and then how they actually get deployed on quantum machines. So hybrid just means you're using a quantum computer to do the parallel stuff, and you're using like a traditional computer architecture to do the things that just can get executed more quickly in series. Another cool thing is precision fermented materials. So this is kind of crazy stuff, but you can this is real, like real crazy. It just sounds crazy, which is why I said it. But like precision fermentation is basically genetically engineering yeast to be able to grow into different materials. So if anyone's, for the bio people out there, CRISPR is genetic engineering tool. You can basically modify things and print genetic sequences. So if you're thinking of advances in medicine, advances in things like lab grown meat, CRISPR is the genetic engineering tool that powers a lot of that. Now, the interesting thing around precision fermentation is that if you have the ability to engineer yeast to be able to multiply and eventually produce itself into other materials, then you can do things that are like actually pretty crazy, right? And we're actually doing this today. So bullet point number 2 is insulin. Most of the world's insulin is actually derived this way through precision fermentation. So instead of it being extracted, which is or like synthesized, it's actually grown in quotes or fermented from yeast, which is really wild. So insulin is the thing, if you're diabetic, you take it to help regulate your blood sugar. But precision fermentation, we can actually use yeast to produce insulin at extremely high purity levels and very low cost. So then the question is like, what else can we essentially grow with yeast, right? And it can petroleum, like red meat cells that are actually just like straight up red meat cells, not a red meat cell proxy. If so, for those of you that are interested in like meat alternatives and things, sustainable fuels, chemicals, like we can just kind of grow stuff, which is really wild. So if any of you guys know a company called Ginkgo Bioworks, like this is kind of their thing, but now there's a lot of activity happening on the periphery around precision fermentation. So really, really cool, kind of very futuristic science, plays into the material science thing I said earlier, but we actually have a lot of TKS students who end up working in precision fermentation. This is like a smaller thing, but I think it's something, if anyone wants to figure out, like basically make a lot of money quickly, this is probably your best route. So thermal management for GPUs. Right now, GPUs are the architecture of choice for these large language model training clusters and basically the most in demand component of the AI supply chain. NVIDIA is a company that makes GPUs, and those GPUs live in data centers, big data centers that you need a lot of water to cool the chips. You have a lot of electricity, obviously, to run the data centers. And it's non-trivial stuff. Like the electricity bill is astronomically high for these data centers, so much so that sometimes there's literally just not enough power available to power these data centers. Think of like the stuff powering OpenAI and Meta's AI, all that kind of stuff, Gemini, etc. And so one of the big problems is the GPUs actually just get extremely hot, right? And their performance is sort of a function of how hot they get, inversely proportional to how hot they get. But also you need to cool the chips or else they'll melt. Like literally they would just melt because they get so hot. So every data center has some sort of cooling system. But NVIDIA basically has made this claim that they're not going to, they're like, NVIDIA doesn't supply any of the cooling systems. They just make the chips, and they're like, we're just going to make the chips as good as we can. We're not going to really worry about the cooling. We're just going to leave that up to other people to figure out. So like right now, if you were to go into an OpenAI data center or something, there's really sophisticated cooling systems in place. The most sophisticated is called direct to chip liquid cooling, which is basically you have a superconducting, or not a conducting liquid, non-conducting liquid that goes over the top of a chip and helps cool it down. But a lot of people who are in this space are looking for more efficient ways of cooling because it's such an important part of the AI supply chain. So a couple like ideas that people are working on are things like drip cooling, where you use like evaporation, a phase change to absorb heat instead of, just like constantly running cold water or some sort of cold fluid over a chip. That's kind of interesting. Another thing is called two-phase direct-to-chip liquid cooling, which is instead of just having like a constant supply of water running over the top of the chip, you have two different phases. There's like a basically like a power phase and then a cooling phase. And that's a much more efficient way to do it, which is really cool. And there's a bunch of other interesting things here, but if anyone's interested in like thermodynamics or just like how to become part of the AI supply chain at large, there are people literally getting paid. I know of this. There's like two people who are making like 10 million a year, and they're just like engineers who are helping figure out the most efficient way of cooling chips. So this is like sort of a very big in demand area. Then there's also the AI kind of like firmware part of this. So being able to offload different, if you think of a data center, just like a bunch of basically like a bunch of towers of chips, being able to allocate different training jobs to different areas of the data center based on temperature profiles, right? So you have like a job that you send over here, which is kind of like pre-cooled. Um, if it's going to be a really demanding job. And if it's not going to be as demanding of a job, then you put it in like this part of the data center, right? Because part of the problem is um, the chips, the heat on a GPU changes over time. It's not like it's just always really high, right? If you like, as it's executing different training jobs or post training jobs, the heat will fluctuate significantly and somewhat randomly. So now there's a lot of work being done where you just have like cooling zones and you can send jobs to different cooling zones based on the kind of the computational workload. So that stuff I think is pretty interesting. Okay, guys. So that's pretty much everything I have prepared. The way I wanted to handle this was like half an hour of me talking and then half an hour of just like kind of jamming out and answering questions. Um, I know everyone has videos off and mics aren't working and all this kind of stuff. So, feel free to put any questions in the chat. If anyone is really interested in learning more about this kind of stuff, or you really want to just like dive into the world of emerging tech and science more fully, go to tks.world. We have a bunch of cool resources on our website. That's our website. Bunch of cool resources. You can apply to TKS through that if you're like, hey, I actually want to like start building projects in some of these areas. But anyway, yeah. And my email is Brandon, Brandon at tks.world. If anyone wants to just shoot me an email and ask any questions. But anyway, what questions do you guys have? Drop them in the Q&A, and it can be about anything. By the way, doesn't have to be about just what I talked about with the emerging tech stuff. It could be about other stuff happening in AI. It could be about like university, whatever's on your mind. Happy to answer. Cool. So we'll give a few minutes. Let's really get some questions going here because that's how we'll make the best use of the last half an hour. So no stupid questions. Just like throw it in, even if it's like I said, more on like the personal side. If you have any questions about the college experience, maybe you're thinking about going off to university and you want to bring that up. That all good. So you have me for another half an hour or so. Okay, so a couple questions coming in now. Let's keep them coming. So first thing is any innovative ideas with AI in medical? Now, the way that I think about innovative ideas in the medical space with respect to AI is there's like easy stuff and there's hard stuff, right? Like that sounds weird, but like it is true. Anyone who's spent time in the medical space, if you have parents that are doctors, maybe some of you want to be doctors, maybe unfortunately, some of us have had to spend a lot of time with doctors. You'll know that things are kind of inefficient on a system level, right? Little things like even medical errors are a big thing where you have hospitals that are really busy places, and sometimes like you need 100 milligrams of this drug but by accident the pharmacy gives you 1,000 milligrams and like it's off by a factor of 10, and that's a really bad thing. So like I think on the quote unquote easy side, one of the cool things about AI is there's like things that can get automated that probably should be automated. I mean, even on a consumer lens, like if you know your head hurts, your throat hurts, or you're having some weird symptom, you can go into ChatGPT and give it your symptoms, and it'll like help diagnose you. I don't recommend doing that, right? But like we've probably all done that, or you know, if I'm a dad, so I have two young girls, and always there's stuff that comes up, and it's like, hey, is this a problem, right? And ChatGPT will help give me a kind of a first line of defense. So yeah, things like patient medical records, being able to search through relevant test data and come up with like more interesting connections between test results and biomarkers. That's all on the easy side. The hard side is more on like the drug development, being able to create like custom therapeutics or gene treatments for cancers, rare diseases, that kind of stuff. Now that's more on the research side, it kind of 0 to 1 breakthrough. The quote unquote easy part of this is it like the hard part about implementing those things is that hospitals and medical practices are very risk averse environments, and generally speaking from like an operations standpoint pretty technology uh, pretty risk averse to bringing in new technology. So I'll kind of leave it at that. But yeah, there's a huge, I could talk for hours on like medical and AI intersection points. Okay, so couple things here. Yeah, so I'm going to go a little bit out of order just to try to string a few thoughts together. If a student's interested in pursuing medicine, what should they focus on from an AI perspective? Like, honestly, you should just learn how large language models work. Like right now, the opportunity in front of anyone is to really understand two things. Number one is like, what are large language models and how do they work from a fundamental standpoint? And then number two is how to apply large language models or other things to neural networks, et cetera, to be able to become better in some way, right? From a research standpoint, from a productivity standpoint. So the advice that I'd give you if you're interested in pursuing medicine, like the most good, it depends on what the motivation is. If you want to pursue medicine because you want to be a doctor, great. Like AI can help you ace your tests and get into medical school and learn things more quickly. Like that's great. That's great. If you want to get into medicine because you have this higher level or higher order goal of like helping save as many lives as possible, then I actually think like being a doctor is probably not the best end to that goal. Nothing against doctors. It's just purely like a numbers game. Whereas if you were able to, let's say, design a new drug treatment for a whole subset of people that have a rare cancer, like that will probably end up holistically improving more lives like in absolute terms. So I think it just depends on what the motivation is, right? And if it is more the latter, then I think you want to just get really down to the AI fundamental details of like how do these systems work, and so forth. So hopefully that answers the question. But I think it's just like these things you can use AI to do amazing things. Kind of an aside, and we do a lot of this like in TKS, but um, like the so the way I think about it is there's three things that are true for you all on this call that weren't true for me when I was in high school, right? The three big things that are true for you that aren't true for me are you can go learn anything you want. Like you can. I'll go into what I mean by that in a second. You can learn anything you want. You can build anything you want, and you can understand what other people have built and reverse engineer it. So let me kind of go double click into each one of those three things. You can go learn anything you want, right? So whether it's learning theoretical physics from MIT OpenCourseWare for free, you can do that. If you want to learn how to build quantum algorithms on a quantum computer, there's like 7 different YouTube creators that make extremely good technical videos on how to do that. So it's like anything you want, you can go learn for free. As long as assuming you're on this call, you have an internet connection and a phone or a laptop, like cool. That's literally all you need. That wasn't true for me. I had to go, like, for me, the only way for me to learn theoretical physics was to either like go to the library and read a bunch of books or go to MIT and take theoretical physics. Like those are the only two options. The the next thing is you can go build whatever you want, right? So this is like mostly true, but in general, even if you're into something like rocketry, like let's say you think SpaceX is cool and you want to build rockets, you can use free tools online to like design rocket parts, test rocket parts, and even like 3D print rocket parts if you really wanted to, right? But 5 years ago, 10 years ago, that stuff cost $100,000 for a license for like, so let's say you build like a rocket part and you want to do vibrational testing on it or like thermodynamic testing on it or something like that. It used to be like $100,000 for a license just for like one of those pieces of software. Now you can use Ansys, you can use Onshape for free online. So that's like pretty cool. CRISPR, you can genetically engineer things. Like obviously you can code things like, so you can go build anything. And then the last thing is you can see what other people build. So this is the open source push where you can get tutorials and demos and everything all the time online for free. And use that as like a way to learn things. So if you combine all of those three things where you can go learn anything you want, build anything you want, and then see what other people have built and use that as a way to like understand how to build stuff, it's really cool because you're operating in this like extremely asset rich environment that no one else in the history of the world has been able to operate in. So like students today it's just like you guys are playing a different game than what I was playing. The game I was playing was like the very traditional school game where it was like go to school, study really hard, get good grades, try to like advance to the next point on the journey. And if you did that really well, like great. And if you didn't, it was really hard to like get back on the path. Well, now it's like a totally different game, right? Because you don't need like university is still great. I'm not saying university is good or bad or anything. But the reality is if you want to learn how to be a like an expert in quantum computing, you can just do it online, like literally. And it sounds crazy, but you can. And you can even build on IBM Qiskit and go develop quantum algorithms like from your bedroom. Um, and then like the layer on top of that is you can actually use AI to help guide your thinking. So one of the things I ran a student I was working with the other day who is really into like the Raptor engine, SpaceX Raptor engine, and wanted to figure out like how it worked, right? And so what we did is we literally pulled up ChatGPT. We're like, hey, I'm interested in developing a simulation that teaches me some of the gating constraints of how a Raptor engine works. I want to be able to tweak different performance variables and see how that impacts the efficiency of the engine. Can you help me design a simulation that does this for free? And literally like, a minute later, right, ChatGPT comes out with like all of the exact steps on how to do that. And it's not, help me do my homework. It's like literally you're going from the ground up of how do you build a simulation to simulate the thermodynamics of a Raptor engine, be able to tweak some of the performance variables, get some cool graphs on the output side so that you can understand how it works. Like wild, just absolutely wild, right? So if you guys aren't taking advantage of some of these tools to follow your curiosity, then you're missing a huge opportunity. So that's kind of that's kind of a riff on the whole on the medical thing. Whereas like if you're interested in drug development, like you can actually go design and develop drugs. Like it's crazy. You can do that today. You need some background knowledge, but that's where the reverse engineering thing comes in. And that's honestly like at TKS, what we do is we teach you how to get really good at that. It's called project-based learning. We didn't make it up. That's a thing that like, if any of you want to go to MIT, they actually ask like, what projects have you built that prove to us that you're a good engineer? Weirdly enough, only 5% of people actually answer the question at all. But that's probably another story. So, okay, let's keep some of the conversations going here. How can teens get involved with these advances? For example, if you were to come up with a solution for something, how would that get noticed? Okay, so there's a couple, like what I was saying before is related to this answer, right? So it's all related. This idea of if you want to get involved with these advances, start building projects in the area that you're interested in. So this is not a plug for TKS. I'm just going to use, because I think we've done a really good job at helping answer this question from a program standpoint. So the way it works at TKS is you come in, It's a 10-month program. The first month, we have all these like learning modules that we've built out, right? What I showed you today is just a very small sampling of like 40 to 50 different learning modules on things like AI and quantum computing and synthetic biology. And so you actually on your own time, you run through these learning modules so that you can get a sense of what you're interested in. And then once you find something that you're really excited about, it's literally that's your North Star is like what seems coolest to me, what am I most excited about. Then we have what we call like the focus process, which is basically just a fancy way of saying you start building projects in that area to get the domain specific skills that you need to become proficient. You start really small with little tutorials and like you don't need to have any background knowledge in any of this stuff, right? But it's literally you start small and build little projects that then compound and turn into bigger projects and more substantial things. And like any of you that have taught yourself computer programming or software engineering know what I'm talking about, right? It's like like let's say you want to learn how to code. You you first find a tutorial on like how to make a game of Tetris or something, right? Which is still kind of hard to do, but you have to figure out a lot of the basics to be able to make the game of Tetris. Like, how do I, what is an IDE programming environment? How do I use the command line? Like all these really basic things. If you have a goal of like making Tetris, you're going to learn a lot of these domain specific skills en route to that goal. And then once you do that, you're like, whoa, cool, Tetris, I made it. It's awesome. I can play it. Like what do I go do next? And then maybe it's something a little bit more advanced and then more advanced, then more advanced. And eventually you get to a spot where it's like, wow, I've just learned all this domain specific stuff. And through that, I actually have ideas of what I can go do with it. Right. So you start off making Tetris and then you're like, oh, okay, I've gotten into AI and more kind of advanced programming. I'm also really into sustainability. Hey, what if I used my knowledge that I've gotten in AI to help better predict the output of like a solar farm or a wind farm? That's actually kind of a non-trivial thing. There's a lot of machine learning that goes into like if you build a wind farm in the middle of Iowa, let's say, you're you know things aren't super predictable. You don't know how much electricity you're going to get out of it. So you can use machine learning to like predict wind patterns and things like that. Anyway, so how do you get involved in those advances is literally just like start building cool projects that excite you in the domain of your choice. And then how you get noticed, this is the really cool part, is it's honestly just find mentors that can help guide you. And this is one of the things that I fundamentally believe is most important for young people to do is if you can find people in your domain that are able to help give you feedback on your projects, that's how you're going to get noticed for your work. So let me give you an example. Let's say you're interested in quantum computing and you spend like 6 months building like very basic. I'm not talking about Nobel Prize winning stuff. I'm talking about like literally like basic tutorial level projects in quantum computing. And then the first time you go try to build something for yourself where it's like, oh, cool, maybe I'm going to use Qiskit to run an optimization problem where like I figure out all of the perfect red, yellow, green traffic light patterns in New York City. That's a crazy hard optimization problem to solve, right? Like literally the most efficient way of going from red to yellow or green to yellow to red on a given traffic light in New York City, right? So that you minimize the amount of waiting time and traffic. Like it's a huge optimization problem to solve. You can use quantum computing to solve that. So let's say you want to do that. Like if you reach out to head of quantum computing lab at MIT and you have that, and it's like, hey, I'm a 17-year-old working on this quantum computing thing. Professor at MIT, would you be willing to meet for 15 minutes to like give me some feedback on my project? I guarantee you like 90% of the time, the answer is going to be yes. Now, if you reach out to them without that project, probably 95% of the time, the answer is going to be no, right? If you just cold reach out to a professor as like, hey, I like the work you're doing. Do you want to hop on a call? Like they're just going to ignore your email, right? But if you have we call it proof of competency. So you don't have to be like PhD level crazy quantum computer person, right? You're like, hey, I'm a 17-year-old. I think this stuff is really cool. I've spent time building this thing. Can you give me feedback? Well, that's how you get a mentor very authentically. And then that mentor, like if they're in a position of power, like running a lab at MIT, they're like, wow, this kid's really good. Maybe they'll hire you for the lab, right? Give you an internship, or maybe they'll say, hey, like this research is actually really cool. You should look into funding opportunities. Or so that's how you get noticed, right? It's all just about that. We call it the flywheel effect. You build projects, you build cool stuff, you get more people invested in your journey, and then those things just kind of compound. Okay, so we have 10 minutes left. Will these actually I'm going to go to one of the questions. I'm going to again I'm going to honor some of the earlier questions here. So Anil, I'm just looking at your question around quantum computing. Where does quantum technology fit? Are there universities or colleges that are offering engineering majors in quantum technology? So I'm gonna assume that by quantum technology you mean like quantum hardware, because the short answer is if you really want to go into quantum computing, like research, um, and you're at university, the best thing for you to study is physics, because you're going to take quantum physics and particle physics if you're majoring in physics, which almost every university offers a physics major. That like we're still in that phase with quantum computing, where the leaps that we have to make are at the physics level. They're not at the application level. So think of it now as like in computing. I don't know if anyone knows Bell Labs. Bell Labs was the company that invented the transistor. They actually, they were down the road from where I live in New Jersey, but they were like the Google of the 1980s, better than Google, like crazier stuff, right? They invented photovoltaic cells, they invented the transistor, they invented radar, they invented like all these crazy things you can trace back to Bell Labs. The people who were at Bell Labs were physicists, like and math people, and some engineers too, but they were like primary science level breakthroughs. And then now when the transistor, by the way, is the thing that like enables the like chip technology for computing. It's like the bedrock of modern computing. Once that was figured out, then we had to figure out how to mass produce it. Then we had to figure out how to mass produce it inexpensively. Then we had to figure out how to increase the number of transistors on a given chip. That's Moore's law, right? And then like as Moore's law climbed and we got better and better, efficiency got better and better. Then, and this is where we're sitting now for the most part, is like the people doing the work are figuring out how to apply that technology to things being creating video games, or things being, the software on an MRI machine. Like, so we're on like the application layer of traditional computing right now. For quantum computing, we're not there yet, right? So what I would encourage you to do is like study physics if you want to, if you are in university and interested in quantum computing. There's going to be like also a lot of hardware engineering, stuff. And my point about being able to go build projects in quantum computing is still true too, but a lot of that stuff is like using very early tools in quantum computing to focus on the application layer. It's like kind of like trying to focus on traditional computing in like year 1 or year 2 of Moore's law, right? It's just like it's changed so much that the application layer has changed so much. um okay. Tasha, I see a question. What colleges have these areas of study? What is the best course of action? Honestly, and this is going to be a kind of an unsatisfying answer here, is like almost none of them do. Well, like if you go to, let's imagine like two ends of the spectrum. On one end of the spectrum, let's say you go to MIT or Stanford. Not good or bad, it just is what it is. On the other end of the spectrum, let's say you go to your community college. Again, not good or bad, it is what it is. The MIT and Stanfords, they actually like, you don't have, it's not like you go and you take all these crazy emerging technology classes. You're going to take largely the same classes at like community college or like MIT. MIT might have fancier labs and you might get into some cooler stuff. If like in hardcore engineering world, like, yeah, for sure. I mean, MIT has like billions of dollars and some of the smartest people. Like it's going to be a different experience, but neither your community college nor MIT or Stanford is going to just like set you up for success with these kind of like frontier technologies. You have the opportunity to get more involved on cutting edge research at MIT, which is I think where it comes in. But look, let me give you my experience because back when I was in university, um, I didn't I was a really good student. I kind of thought I wanted to do mechanical engineering, which is what I ended up studying because I liked building stuff when I was in high school. But I didn't have like a super strong thesis for what I actually wanted to do with mechanical engineering. I basically just said like I want to be a mechanical engineer. That's as far as I got. And so at school, like I spent the first 2 years just like taking a bunch of 101 level classes, which is what most people did, right? It's like you get to school, you have to take a bunch of these like kind of basic classes. You have to learn thermodynamics 101 and this and that and whatever. And then like your third year, you kind of get a little bit more specialized. Then like your fourth year, maybe you get into some cool research stuff or whatever. The most dangerous people, and I mean dangerous in like a good way, because college is kind of a competitive environment. They're the ones who enter university with a stronger thesis for what they want to use the time and resources to go do. So if you think of like, I'm a little jaded just because I've paid a lot of money to like flashy universities, and so universities are business. Um, let's say you go to Stanford, right? Stanford loves to advertise, hey, we've got like 70 Nobel Prize winners on campus. We've got whatever, like a $20 billion endowment. We've got all this research. We got all these fancy labs. We got it like, and it's all true and it's all great. The problem is like you're essentially paying. It's like a very fancy gym. You're paying a really high membership fee to go to this gym with all this crazy cool equipment, and but if you don't know how to use any of it, or you don't actually like get trained on how to use the equipment, then like you're not getting your money's worth from your gym membership. And so college is kind of the same way where you go, and the best way to take advantage of the like being at college thing is to go in with some sort of idea of what you want to use your time to go do. So for me, for example, if I'm being like, reflective, instead of just showing up and being like, okay, I want to be a mechanical engineer, like train me, I would have gone in and say, I'm really interested in humanoid robotics. I want to get connected to this robotics lab at MIT so that I can start doing research from day one. Oh, and by the way, I've already done some projects in robotics to prove that like I'll be able to hang with the researchers and stuff. Like I would have basically gotten 3 more years of cool stuff in college if that was my approach. So Tasha, to your question of like what college, the best course of action is to spend, doesn't have to be a long time, but spend at least like a couple of weeks to months before you get to college figuring out like how you want to use the platform to boost your signal. And then the other thing is like you should just study what you're most interested in. It doesn't even have to be STEM, to be honest. But if making progress in emerging tech and science is the thing, I would first like while you're still pre-college, I would ask yourself the question like, what am I actually interested in? And then you can go into college with a little bit more intentionality. Okay, Nadia, I see a question. Most of these areas you talked about, and I think this will be our last question, just for time reasons. Um, most of these areas you talked about are or will be new fields in STEM. What would you recommend for schooling if I'm interested in a newer field that is not as developed or clear cut as a major? Okay, so exactly same thing in that answer. Now, just to be a little bit more practical, here are majors that I think are going to be extremely in demand for emerging tech and science. Um, Physics, chemistry, biology, like foundational theoretical and math, like those four, you can't go wrong. Physics, chemistry, biology, math. You can't go wrong with those four. From a research and first principle thinking standpoint, all four of those connect to all the things that we talked about, except for maybe biology and chemistry, but like they connect to some, right? Depending on what you want to do. On the engineering side, I think material science or like chemical engineering, mechanical engineering or robotics engineering, and and probably like electrical engineering are the three engineering things that are, and one lens to look at this through is like AI resilience, right? AI is going to supplant some of the traditional research capability and or like technical capability, replace programmers, things like that. And so I think like another smart lens to put on it is like, how do you develop AI resilience in what you're studying so that you can't be replaced by the machines or the AI? So we can talk a lot about more about this. Look, if anyone wants to keep found this cool or like send me an email, Brandon at tks.world. I will respond. Ask any more questions you have. I can even hop on a call if anyone wants to learn more about, like joining TKS. I think if you are interested in this stuff, like building projects is undeniably the way to go. Um, and it's not even like a TKS thing. Like I do alumni interviews for some of these schools and stuff, and the amount of students who want to study engineering or want to study, and it's like, cool, what projects have you built? And the answer is like none, is astounding to me. And I don't say that as a criticism. I say that as like an opportunity for you guys. If you want to, like, if you want to get more into these areas, that is the move. So do it on your own. Do it with the help of a program like TKS. I would just really encourage you to not let this moment slip away. This sort of technology moment that we're having. Cool. All right. Well, thanks everyone. Sydney, thanks for having me, and I hope everyone has a great rest of your evening or day, depending on where you're at in the world.
Thank you.
Thanks.